Hi, so my name's Eyad. I'm the Chief of AI Research at Humans in the Loop, a Bulgarian startup focused on doing manual labeling for large-scale machine learning projects. I had the R&D department, and today I'm going to be talking about the current state of AI, namely deep learning versus neurosymbolic architectures. So the way I'm going to be structuring this talk is the following. First, I'm going to be talking about the limitations of deep learning from the statistical as well as the mathematical perspective. Then I'm going to be talking about some failure cases of deep learning in computer vision and natural language processing. Finally, I'm going to be very briefly touching on neurosymbolic architectures and giving some examples of how they can help us overcome the pitfalls of deep learning. So first of all, the statistical limitations of deep learning, misconceptions about probability and statistics, what is actually probability and statistics, and the axiom that probability is always conditional. So misconceptions about probability and statistics. Probability and statistics are used to explain or to quantify the uncertainty in that which we do not know, as quoted by Dr. William Briggs. So what does that definition mean? It means that probabilistic models and statistical models are used to quantify uncertainty in some data set, but they are not used to represent knowledge. Statistical models can never be used to represent knowledge, at least certain knowledge. Probability is not real. It's not physical, and it does not exist in real life. It only resides in our intellects. This is the point where we need to firmly grasp the difference between epistemology and ontology, what we know or what we think we know, and what actually is. So probability is always conditional. Probability is always conditional on the premises we feed in to the model. So if I say, for example, what's the probability that a coin is in my left hand and not in my right hand? Saying 50% is not exactly accurate. Why? Because I have not stated with 100% certainty that there exists a coin in either of my hands. So you cannot base your statistical inference off of a condition that I never mentioned. I think we often tend to ignore this axiom. So there's no such thing as unconditional probabilities. I think the inability of current deep learning models to cope with variations of the input is because the inputs are not grounded to some ontological priors, something that actually exists. So if we take, for example, a computer vision model that is supposed to classify an image, whether it is a car or not a car, the pixel values, the inputs, they are not actually grounded to some real knowledge, and the weights we calculate that correspond to how each single input or each single pixel contributes to the label, these weights, they're not conditional on something deterministic or something ontological, like I said. So for example, they are not conditional on the geometrical structure of the car. We like to think they are, but they're not. And I'll be talking about this in the failure cases in computer vision models when we're talking about the feature detectors or the kernels. So next, we have the mathematical limitations of deep learning. The optimized version of the loss function we get after training a deep learning model, its weights are exclusive only to the data set at hand. Why is that? Well, the reason is when we're doing forward propagation and we calculate a single value of the loss, we then, in back propagation, we then try to propagate this single value to each node in order to know how each node contributed to that loss. And we do that by calculating by doing a partial differentiation in a chain rule manner, which means that the weights corresponded with each input or with each node, it's not absolute. It does not just exhibit the correlation between, let's say, the node or the input and the corresponding label. It actually has embedded in it other correlations as well. So it's not absolute, like I said. It's just it's more relative. And this is exactly what chain rule is about. So node X, we're trying to calculate how much node X contributed to the loss. But node X actually receives input from node X minus 1, node X minus 1, and the whole layer, the weighted sum of the inputs to node X from the previous layer. So the weights when you change the input or when you introduce more variations to the input, you lost actually this relative correlation or relative association between the input and other inputs. So you basically have two correlations. Let's think about it like that: a correlation or an association between an input and output, and between one input and all the other inputs. So interassociation or between inputs. The fitting function, while maybe continuous, it has a very restricted domain over the features values, which means that deep learning models mostly capture spurious correlations. So from a calculus perspective, we have a continuous function, but the problem is the domain of this function is not from negative infinity to infinity, so it's not capturing all the possible values of each single feature. It's just capturing a small range of, let's say, feature 1, and a small range of feature 2, and a small range of feature 3. So this restricted domain means that we lose some information, or we lose some information about inputs that were not included in the data set, but might be relevant to the same domain we're trying to model. Next, we have bias and variance. I think there are only two ever states for any statistical model, of which deep learning models, of course, are a subset. Either it is biased or it's not working. Why? Let's talk first about being biased. The reason is that for a model to capture frequency-based correlations, the pattern in the features must appear more frequently among the data points. So basically, we just need less variations among the observations, and this increases the bias. Like I said, we need the pattern among the features to be repeated as many times as possible, so that when we calculate the number of repetition against the relative frequency, we get a high number, so we can capture the pattern rather than just capturing noise. About the variance, so at the same time, we want our model to capture as many variations of the input as possible, because this enhances the model's generalization ability. We also want our model to not be biased to one class over another or one range of values over another. Naturally, we want more variations introduced to our features. Like I said, to capture more examples and more data points, so that our models can generalize better. But doing that results in modeling the noise in the data set rather than the actual repeated pattern. So if you, like I said in the previous slide, if we have, let's say, if the input is not repeated like a lot of times, then the frequency or the correlation between a single input and the label, or the range of values in case of regression, when you divide that by the relative frequency, you get a very small number, so it becomes insignificant. So adding more variations should, in theory, make our model generalize better, but in statistics, it just doesn't help. And it leads to a non-working model because it starts modeling the noise rather than an actual repeated pattern. Why? Because the pattern is minimalistic in this example. So failure cases of deep learning. Let's talk first about computer vision, then language models. So failure cases in computer vision. Kernels or feature detectors do not represent the geometrical structure of the objects. Let's take an example. Do vertical lines, when we're trying to detect vertical lines, do these vertical lines have preserved the geometric structure? The answer is no. Why? It's because this vertical line detected by our kernels do not have the geometrical equation of a line. So poor knowledge representation leads to poor extrapolation. It's still a spurious frequency-based correlation computation. Why spurious? Like I said, because it is not conditional, and it's not conditional on ontological premises or ontological priors. Frequency-based correlations, because you basically try to model the repetition of a pixel value or a range of values of a pixel or a feature in correspondence to a specific label. How do you visualize that? Photoshop let's say, for example, Photoshop a tree to the background of a car classifier and train the model long enough for the tree to become the car. What do I mean by that? Basically, if you Photoshop a tree to the background of a car classifier, and you train your convolutional network model, you just what happens is that the pixels of the tree are constant with respect to the label, which means that they will become the main features, the main reason the deep learning model thinks that this specific image is labeled a car, because the repetition of the pixel values of the tree are always consistent across all images. So in language models, the problem with language models is that they use empirical Bayes, and empirical Bayes estimates the prior distribution from the observation data set. This, of course, does not make sense in language models, because at least linguistically, priors means that you should have your prior knowledge prior to observing the environment or looking at the observation data set. Latent space representation and cosine similarity are metrics whose input is the frequency of words appearing together in the same text, but it does not explain how actually these two words or these two entities relate to one another. Example, in higher space, in a high dimensional space, you see words such as school and bus very close to each other in the high dimensional space. The distance similarity between them is very small, but it does not actually tell you that how they relate to each other, or how they are used in language. I'll be talking about that in when I'm touching on neurosymbolic architectures. So another thing is that the attention mechanism in transformers has no grounding in cognitive psychology. It has the attention mechanism used in transformers has absolutely nothing to do with cognitive psychology. I ground attention models in cognitive psychology to one of two things: either the manipulation of knowledge in mental states. So, for example, trivially, let's take an example. We're talking about food, restaurants, eating. Your brain can like separate this from everything else. So when we're talking about, or when we're thinking about food, eating, restaurants, stuff like that, your brain is probably not thinking about swimming or jet skis or anything irrelevant to, like I said, eating or food example. So next, the objective of the agent in the environment through active inference. Basically, let's assume our agent is trying to cross the street. So it's trying to change its external state, means it's moving through the environment. It has to filter like acting on the external state and acting on any other states. So to recap, the main problem with deep learning is that deep learning, like any statistical model, does not represent factual knowledge. It only quantifies uncertainty. This means no priors and no premises. This means that the probability is conditional axiom has failed. This leads to poor extrapolation ability, let alone generalization. So the solution: we just represent factual knowledge about the world, or if we're talking about a narrow domain, we just represent factual knowledge about that domain. And we then base all our probabilistic inference off of this knowledge. Key solution is neurosymbolic architectures. So a quick example in language models, when I talked about deep learning not being able to tell how a school and how a bus relate to each other, let's take an example. We define a school as a place or sub-environment, define a bus as an object that changes the agent's external state from one sub-environment to another. This means that our model can extrapolate to all buses, because if one bus can change the external state of the agent from one sub-environment to another, then all buses can do the same functionality. And we can generalize to all vehicles, not just the bus. In computer vision models, I'm not a computer vision researcher, but I think that it's more fitting to study the geometrical structure of objects in the 3D space, then do the projection of these features on the 2D space. I think that would be a step towards more ontological knowledge representation, and then we can use this to base all our probabilistic inference based off of this knowledge. And we're going to be satisfying the axiom probability is always conditional. Thank you and stay safe. Bye.